Continuing with quantum numbers, yesterday I was explaining to you what each of the quantum numbers stand for. And so again, N is the energy level. So if we're looking at an electron in the 1s, then N is 1. If we're looking at an energy level in the 2p, then N is 2. Okay, so that one's easy. It's just energy level. And the quantum numbers are easiest, in my opinion, if you relate them to electron configuration. So the second quantum number, L, is the orbital shape. It's called the angular momentum quantum number, but really it's the sublevel. So that you just have to memorize that for L, for the S is 0. So instead of saying a 1s orbital, you'll say 1, 0. Instead of saying 2s, it'll be 2, 0. Instead of saying a 2p, it'll be 2, 1. So you just have to memorize that S is 0, P is 1, D is 2, F is 3. All right, so the L values can never be bigger than N minus 1. Right? They never can be bigger than N minus 1. And that's because at the first energy level, there's only an S orbital. So it'll be 1, 0. There's no such thing as 1, 1, because there is no such thing as a 1p. Okay, it doesn't exist. So L can never be higher than N minus 1. At the second energy level, we can have L to be 0 for 2s. We can have L to be 1 for 2p, but there's no such thing as 2, 2, which would be a 2d. Okay, it doesn't exist. All right, so L, just memorize, S orbitals are 0, P's are 1, D's are 2, F's are 3. That's just the address instead of calling it S, P, D, and F. All right, just a number. Then for the M sub L, they will equal between L and minus L. Okay, so for M sub L, think of it as the orbitals. So for a p orbital, instead of calling it px, py, pz, we're going to call 1, 1, 1, 0, and 1, negative 1. So M sub L values are going to range between L to minus L, going through 0. So for a d orbital with 5 separate, or d sublevel with 5 separate orbitals, we had those ways in the workbook assignment. It was like d, x, y, and y, z, or whatever, all those. Well, now they're given numbers. And since d is 2 as L, so at d, L equals 2, then for M sub L, we can range from 2 to negative 2. So one of these will be 2, one of these will be 1, one of these will be 0, one of these will be negative 1, one of these will be negative 2. Okay, so that is just specifically designating them as number values for the 5 different Ds. And then for Fs, since there are 7 different orbitals, they're going to range from negative 3 to positive 3. Right, so I think that's all on that page. Okay, so then if we were going to write the quantum numbers for the 2 electrons in helium, all right, helium's 2 electrons are in the 1s. We did this yesterday. So the 1 electron would be in the 1, 0, 0 plus 1/2, and the other one would be in the 1, 0, 0 minus 1/2, because the quantum number M sub S is spin, and in the same orbital, one has to be spinning clockwise and one has to be spinning counterclockwise. Well, now instead of drawing the arrows, we call one of those plus 1/2 and the other one minus 1/2. Okay, so those 2 electrons, they're both in the 1s orbital, but they have a different 4th quantum number, because the Pauli exclusion principle says no 2 electrons can have the same 4 quantum numbers. So they have to be different in the 4th quantum number. All right, so continuing on to a bigger one, looking at carbon. So in the 1s, there's a 1, 0, 0 plus 1/2 and a 1, 0, 0 minus 1/2. So we're just shortcutting it by putting plus 1/2 comma minus 1/2. Some people do plus minus 1/2, meaning that they're both in there. So that just shorts us writing a little bit. Instead of writing 1, 0, 0 twice, we're just saying that there's 2 in there. One of them's plus 1/2, one of them's minus 1/2. Same thing with the 2s for the carbon. There's 2 electrons in there, so we can just say 2, 0, 0, 1/2 and minus 1/2. Or you can write them all out. You can write 2, 0, 0 plus 1/2 and then 2, 0, 0 minus 1/2. All right. Then for carbon, in the 2p, there's only 2 electrons when we're looking at the periodic table. So I don't have a number periodic table, but on my picture periodic table, so looking at carbon, it's the second one over in the second energy level, so that's 2p. Okay, so for 2p, we have only 2 in there. So this one we have to write out separately. One will be 2, 1, and then you can pick which of the 3 p orbitals you want to have for your m sub l. You can have 1, 0, or -1. So I put the first one in -1, and then by convention, you always put plus 1/2 first. And then I put the second one in a second orbital, so it's like the boxes, okay, the 3 orbitals. So one's -1, one's 0, one's +1, it doesn't matter which, but I'm just putting 2 in there. So the second electron in the 2p orbital for carbon also has to be spinning clockwise plus 1/2. So it's 2, 1, 0 plus 1/2. And that would be carbon. So yesterday I'd asked you to try to write the quantum numbers for gallium. And so this would be all of them that we would have. The 2 in the 1s, the 2 in the 2s, the 6 in the 2p. So those would all be 2, 1, 1 plus 1/2 minus 1/2, 2, 1, 0 plus 1/2 minus 1/2, 2, 1, -1 plus 1/2, -1/2. That would take care of the 2p's. And then continuing on down, we would have the 3s's, then the 3p's. Okay, that would be 3, 1, 1, 1/2, -1/2, 3, 1, 0, 1/2, -1/2, 3, 1, -1, plus 1/2, -1/2. That would take care of all the 3p's. Then we would have the 4s's, the 2 of them, 4, 0, 0, plus 1/2, minus 1/2. Then we would have the 3d's, and there it's full for gallium. So we'd have 5 separate orbitals. And so all of them are 3d, 3, 2. But one of them's 2, one of them's 1, one of them's 0, one of them's -1, one of them's -2 for m sub l. And then all of them have 2 in it, so plus 1/2, minus 1/2. And then the last electron in gallium is in the 4p. And so it has to be 4, 1, but then you can choose which of the m sub l's you want to put it in. Do you want to put it in the -1/2, 0, or the plus 1, I mean the -1, the 0, or the +1, and then it would be spinning plus 1/2. And that would be all the quantum numbers, all the addresses for all of the 31 electrons in gallium. Okay, so then other practice type questions, just understanding what orbitals are, what quantum numbers are, relating them to the orbitals. This first question, give all possible m sub l values for orbitals that have the following: L equals 3. So again, I always think about what that means. If L is 3, we're talking about which orbital. So again, S is 0, P is 1, D is 2, F is 3. So I'm talking about in the F sublevel. And I know that for m sub l, the values range from L to minus L going through 0. So I know that there are the possible values of 3, 2, 1, 0, -1, -2, -3 are my possible M-sub-L values when L is 3. Okay, for B, when N is 6 and L is 1, again, relating that to the electron configuration, N is 6 is the 6th energy level, P being 1 means that L being 1 means that it's the P orbital, 6P. So for this one, the M-sub-L values, again, are from +1 to -1. So M-sub-L could be 1, 0, or -1. Okay. For the second question, it says, write the 4 possible quantum numbers for the 4 highest, which are the outermost electrons of selenium. So looking on the periodic table, finding selenium, I see that it's in the 4p level and that there's 4 electrons. So selenium ends in 4p4. So those are the highest energy level electrons. The lowest energy electrons are the ones closer to the nucleus. So the outermost electrons in selenium are in the 4p. So we have 4 for N, L is 1, and then I can choose. So my first one, I'll put in the 1, and it's spinning 1/2, just like the picture here. Then the second one, I'll put in the 0, and it's spinning the same way. The third one, I'll put in the -1, and it's spinning the same way. And then my fourth one, I can pick where I want to put it in which of those 3 orbitals, but it has to be spinning -1/2. And that would be the 4 quantum numbers for the 4 highest energy levels in electrons in selenium. Okay, so then I gave you another paper to try.